Hello and welcome to Office Hours with Bill Jennings. This is a continuation of our last video talking about parent graphs. Now we're going to talk about individual transformations for each of those. Well, we're going to pick on a couple of different parents, but we're going to offer up what are our different transformations that we could make to a given graph. So I want to start with, I'm going to pick on our f of x equals x, kind of go back to that basic function and talk about how many different ways we could think about this. So f of x equals x, we all know is this nice little straight line here going through the origin as such. And we could say it had a major point, 0, and from here we had these types of behaviors from our major point. And if somebody came along and says, hey, you relocate major point over here, we could recreate that graph. So let's see what we can pull off moving that graph around. So I would like to consider f of x equals x plus 2. Now we all know from graphing y equals mx plus b, we know that the y-intercept is 2 and a slope of 1. We can graph it. But I want you to reconsider it as potentially a transformation of taking, I have an original function f of x equals x, and what I'm doing with my original f of x, and I'm adding 2 to it. So take the original base function, add 2 to it at the end. Let's plug some numbers in and see what happens. If x is negative 2, f of x is going to give us back a negative 2. Then, if I take f of x and add 2 to it, you could say that I'm shifting this graph up 2 and it goes to 0. So where I was at on the graph, f of negative 2 created a negative 2, but I'm going to do a shift, an upward shift of taking it up to here. Then if I go to negative 1, that would have produced back a negative 1. Negative 1 plus 2 is going to give me 1. So I was here, and I shifted it up 2. And then it's 0. You could say that I had 0. Well, 0 would have given me back 0, but then 0 plus 2 would have given me 2. So you could say this line shifted up 2 also. So I want you to see this as basically taking my original line and then saying, you know what, let's just grab that guy and let's just move him up here. Just literally am moving it straight up 2. Notice what happened to my major point. What I want you to focus on is major point went up 2. From major point, I still have the exact same behavior pattern coming from major point. So let's put that into play for one of our other functions. Now let's consider a transformational shift on my x squared function. So I have my x squared, and I could talk about what that parent graph looks like. Well, that parent graph, x squared, I know starts at the origin and has behavior from major point that goes right 1, up 1, and then from major point it goes right 2, up 4, and it goes doesn't just go back 1, it goes back 1 and then it goes up 1, so it's going to be here, and then it goes back 2 and it goes up 4. So I know that my parent graph looks something very similar to that, and there should be arrows on the ends of both of those. Now, if I take that exact same knowledge that I just gained from my basic f of x function, we were talking about I have the original function plus a constant. It could either be plus a constant or minus a constant. I've got a minus coming in just a second. I'm going to take major point and I'm going to relocate major point up 1. Now, nothing has changed on the shape of the graph. I've just relocated major point to go up 1. So from here, I've got up 1, and then my behavior of the graph is going to behave exactly the same from this point. Now it feels like it should look different than this, but this is exactly what has happened. Now I don't have any other transformations going on, but I could look at this as being, it looks like it should always stay far apart. It looks like it's getting up in this region, it looks like it's getting close together, but it's really not, because the shift is not in, the shift was up, and so you could say this point relocated up 1, that one relocated up 1, up 1. What I really want you to concentrate on, though, is the major point. Let's move, I want you to move the major point, relocate major point, and then take the behavior from there. That's how I want you to see it. Now, f of x equals x squared minus 2. I think it's always a good idea to put what is our parent graph on our graph, and then we can drag it around and make it move around. So this is my parent graph. of x squared. So that's who x squared is. And notice now I'm going to subtract 2. And think of it as being f of, you have x, you've got f of x, and then you've got f of x minus 2. Essentially, this is f of x, and you're subtracting 2 at the end of it. So when you plug in that 1, you'd get, this is really 1 squared, which is 1, and then you're subtracting 2. So that's going to do what? Well, it's going to be 1 minus 2, which is going to be a negative 1. And it's really just going to relocate right on down here. Notice that what happens, so let's focus on major point. Major point is going to go down 2 and relocate to this point. From major point, my behavior from major point says I go right 1, I go up 1, and that's that point. From major point, I'm going to go right 2, and I'm going to go up 4. 1, 2, 3, 4. And then I would go back 1, up 1, I would go back 2, and up 4. You could look at the symmetry there. And so I'm going to end up with a graph that's going to look like that. That is what's called a vertical shift, up or down. And so we saw it happen with the linear function. We've seen it happen with the quadratic. I could apply it to x to the third. I can apply it to the absolute value. I can apply it to any one of those parent graphs. All I got to do is move major point up or down. This is not a left or right move, up or down, and then the behavior remains exactly the same from the major point. Next one I want to talk about is a horizontal shift. And the best example for horizontal shifts, we can do horizontal shifts on any of the other graphs, but I think the best example for horizontal shifts happens inside the square root function, because actually we have a limited domain on the square root function that actually changes when I put things inside of that radical sign. So let's kind of forget about transformations for half a second, and let's just talk about identifying the domain. Remember, my parent graph of f of x equals the square root of x had a domain of 0 to infinity. The domain, remember, that's the x values that we can put in. It had a graph that looked like this. I went 4, 2. It had a graph that looked like that, and it had a lot to do with the fact that you can't put a negative number in. Let's consider this function that I'm talking about right here. It says the square root of x plus 1. Now I want you to notice that the square root of x plus 1, this is a completely different animal than the square root of x plus 1. That square root of x plus 1, well, that's f of x plus 1. That's the one happening after the fact. This one is happening inside. It's kind of like x plus 1 hanging out inside. So it's a world of difference. If you see this, whoops, if you see this, what we had going on there was we had that transformation that was the up and down that we had just one moment ago. That was the vertical shift. So let's get rid of these guys and let's come back to focusing on our task at hand here. So square root of x plus 1, what would the domain be? Well, x plus 1 has to be greater than or equal to 0 by the definition of this square root. So x has to be greater than or equal to a negative 1. Well, that domain for this would match up with a domain that starts at negative 1 and goes on. So this x plus 1 is actually a shift to the left one. So we had the addition that was outside the function went up and down. And now if we have an addition that happens inside the function, we're going to go left or right. Now pay very close attention to the fact that this x plus 1 actually goes left 1. If it would have been, x plus 3, we would have gone left 3 because of that. That's that greater than or equal to would have come into play and made it go that way. Your book's going to talk about as being x minus c, and c is your shift, and trying to put it in that negative. It can kind of confuse you a little bit. The key thing is that I like to talk about how do you get back to 0? Major point happens at the origin. So how do you get back to the origin if you have an x plus 1 hanging out? So when you have this x plus 1 hanging out here, how do you get back to 0? You get back to 0 at negative 1. So my major point is moved, so we want to talk about this as being a left move 1. So my major point relocated here. From major point, my movement is right 1, up 1, so there's that. From major point, I go right 4, and then I go up 2, so I'm right there. My graph's a little overlap because I got a thick pin going on, but that's what that's going to look like. I moved it left 1. Okay, Let's talk about square root of x minus 2. Square root of x minus 2, okay, x minus 2 has to be greater than or equal to 0. I'm just thinking about this. This is not about transformations, talking about domain. That means x has to be greater than or equal to 2. So my domain of this function is going to be here. Can you see that that is a transformational shift of right 2 from my parent graph? My major point used to be here, and I'm going to shove it to the right 2. So let's take that major point, relocate him to the right 2, and once I relocate that major point to the right 2, from here I can just recreate the square root graph, and the square root graph has behavior from the major point, right 1, up 1. Right 4, that's going to take me out to 6, it goes up 2. And I could go right 9, which is going to take me out to 11, and goes up 3. So I end up with a square root graph that looks something roughly like that. That is a horizontal transformation. Notice that horizontal transformations happen inside. So other examples, if it had been x minus 2 squared, that would have been a left-right shift. It had been x squared plus 3, that would have been an up and down shift. And if I talk about absolute value of x minus 1, that is a right shift of 1. Sounds backwards, but how do you get back to 0? You got to put in a plus 1. So see the difference between those. And this, if this is absolute value of plus 1, that's going to be an up 1 shift. Our next transformation is going to be a reflection across the x-axis. And what that reflection across the x-axis is just applying a negative. And I want to focus on the fact that this negative is happening outside of the major piece of this function. There's a difference between having a negative x squared and having a negative x squared. It gives you, this will always give you a negative output. Think of the we've talked about the domain. You can put any x in that you want, but let's talk about the range. This function will always give you a negative output because no matter what number you put in, you square it, you'll get a positive number. This negative on the outside is saying then take its opposite, which will then make always a negative number. So it's this reflection across the x-axis. So every number that was positive, if we think of it as being a f of x, and then let's take its negative. Well, if I put in a 2, f of x squared would have been 4. Apply the negative, you get negative 4. If I had to put in a 3, 3 would have given me 9, and then when I apply the negative, I get negative 9. Negative 2 would have given me still 4, because negative 2 squared makes positive 4, but then when I apply the negative, it's 4. So we end up with major point hasn't moved on this. Major point's still in the same place, because 0 is still at 0. But instead of coming up with this function, we have a reflection that goes around the x-axis, and so my behavior, you could say my parent graph did this kind of behavior, just like such, and I'm going to take this graph and I'm going to then just reflect it across the x-axis. So major point stays in the same place, and I'm just going to give it this behavior that goes like such. And so this would be a reflection around the x-axis. So my final graph looks like that. I had my parent graph in there. Should have used a different color there. Okay, coming on down to applying this to another function. So again, my parent graph could have been we've seen this a couple times now. We've got our square root function. That's what the square root of x looks like. Now, if every output, I had an output that was here, but then if I apply that negative after I've taken the square root, I'm just going to get this result. And after I've taken the square root of 4, square root of 4 is 2, then apply the negative. Once I apply that negative, it's going to bring that value down here, and then this is going to bring it down there. Notice major point hasn't moved, but I've just taken that guy and I've just flipped it right over that x-axis. So, whoop, hard to see it through my arm when it comes down that way. We get this guy going on there. The next transformation would be across the y-axis. Now, if you have y-axis symmetry like you have in x squared, you kind of lose this feature because it would reflect across the y-axis and still be itself. But we can pick on the square root of x and x to the third for this transformation and see how it comes together. So this is saying that I'm going to take the square root of negative x. And I think I like to pick on this one because, again, we're dealing with a domain issue. If I talked about the square root of x, we said the domain was 0 to infinity. But if I talk about the square root of negative x, if I put positive values in and I take its opposite, it isn't going to work. So my domain in this case is actually going to be negative infinity to 0 the other way. So it kind of just turned the graph around the y-axis. So the negative on the outside of the function, remember that the square root of x negative that way, turned it over the x-axis, and if I put the negative on the inside, I'm going to rotate it around the y-axis. So I've turned my domain around. Again, in this case, major point hasn't moved. All I've done is I've said, well, you used to go this way, and instead of having you go that way, I'm just going to flip you. It's a reflection right around the y-axis, and so my final graph is going to look like this. Now, if you wanted to get really tricky, I suppose you could take a negative square root of a negative x, and you'd end up with a graph that ends up down here, wouldn't you? So we have to be able to make any of those graphs work. Okay, so if I have x to the third, again, if x to the squared is a horrible example here, because if you reflect it around the y-axis, you get the same graph back. My parent graph looks like this, and with a little bit of practice, you'll get these parent graphs. You just need to see them real quickly in your head. So that's my parent graph. And if I apply this negative, I'm going to, now this negative is actually inside, and so I'm going to visually see this as being a reflection around the y-axis. Actually, it's going to go there because what was over here is now going to go over there. And so what was here is going to go there. 0 stays in the same place. This guy is going to go here, and this guy goes here. And now I can come down and draw, try and see through my arm better this time. And there we're going to have our line that goes there. So I'll clean that up just a little bit so we can see it a little bit better. There we have our transformation as it would come through that point. One could argue that negative x to the third is going to be the same thing as negative x to the third. A little bit of algebra, you can actually see that happen. And so you would get the same transformation if you went up and down as if you went left to right. But that won't always be the case when we start to apply other transformations at the same time. The last transformation that we want to talk about is shrinking and stretching. And we could debate for another 20 minutes whether or not stretching or shrinking is which one's which. But I want to talk about focusing about what it does to the y value. It'd make it twice as much or half as much. And we'll let the textbook writers talk about whether you've actually stretched the graph or shrunk the graph. Let's focus on the output, because this is where this constant comes into play. Notice that if I put a constant out in front, I end up doubling the output, because if I had the graph x, absolute value of x, and then I said, you know what, let's just times it by 2. I mean that to be times, so I'll make it an asterisk, so it's like times 2. So if I let x be 1, absolute value of 1 is 1, and then I want to double the output, it's going to be 2. If I said x was 2, well then the absolute value is 2, and then I want to double it, so that's going to make 4. 3 would be 3, doubling it would make 6. So my parent graph was actually a straight line that looked something and resembled something like that. That is the absolute value of x. This 2 out here, the major point has not moved. This is not a shift. It's a doubling of the output. So from major point, I have major point. I used to go over 1 and up 1. The over 1 stays. It's the output that's doubled. So the doubling of the output makes it go to 2. I go over 2, and I used to go up 2. But that's the part I double. I double the output. It now goes up 4. I went over 3, and I used to go up 3. I doubled the output. It makes 6. And so we can see that we end up with this guy going on here, roughly about like that. Now, that's actually called a stretch technically, and the reason why it's a stretch is because you stretched it up, up, up. Some people see it shrinking to the y-axis. It's actually a stretch because I've made the output twice as large. Let's consider what would happen if I took half of x. So again, my parent graph is going to be here, and I have my major point, and so if I took x, and then I took the absolute value of x, and then I took, and I says, let's cut x in half. Because that's technically what's happening with a half. So if I start again and I say, well, let's put in 2, absolute value is 2, cut that in half, you get 1. If you put in a 3, you get 3, cut that in half, you get 1.5. Let's see if we can put that on a graph. Well, major point hasn't moved. And I haven't moved major point. This is going to be a shrink, and the reason why they call it a shrink is because it shrinks to the x-axis. Some people think this is a stretch because it gets flatter as it goes out. Don't worry about the stretching and the shrinking. Really want to focus on what happens to the output. I used to go over 1, and I used to go up 1, but I'm going to cut that output in half. I went over 2, and I used to go up 2. I'm going to cut that in half, so I'm only going to go half as tall. I went over 3. I used to go up 3. I'm going to cut that in half, so I go that way. So I end up with this graph that is half as tall. And so that guy goes there, doesn't he? So we're going to get this guy going something like that. So that's going to be our stretching and our shrinking. That was the end of our transformations. Got one more video coming up for you. We're going to put them all together, and there's an order to the transformations that becomes important, because we could have something that shifts left, goes up, shifts or rotates around the y-axis. We can have all kinds of things going on. So we'll explore those next.